Hi everyone, I'm Andrea Lenzi, a PhD student from Computer Science Department of Sapienza University of Rome. With Professor Paola Velardi, we have submitted to the ACM SAC 2022 conference the paper Collaborative is better than adversarial generative cooperative networks for topic clustering. In the following presentation, I'll try to illustrate the key aspects of this work. Topic modeling represents a popular technique to learn the thematic structure of large collections of unlabeled documents without human supervision. Essentially, it's an unsupervised natural language processing task. In the last years, different neural network models have been proposed to solve this task, like autoencoders with their variants and generative adversarial networks. However, these approaches present some problems. Indeed, opposing agents in GAN could cause problems of convergence, while, on the other side, autoencoders could overfit on the training data. In this paper, we propose a novel topic detection strategy called Generative Cooperative Topic Modeling, GCTM. Generative cooperative topic modeling consists of 4 sequential phases. At first, we have dimensionality reduction. In this first phase, we try to extract the most significant latent features and learn compressed representations from text documents. Afterwards, there is agglomerative hierarchical clustering. In this second phase, we try to obtain clusters of similar documents, starting from the previous compressed vectors. Later, the third phase consists in the summarization of the most relevant words from the detected clusters. Finally, the last phase of GCTM consists in the optimization of the extracted topics through word embeddings computed on the original corpus. Next, all the different steps will be explained in more detail. At the beginning, in the dimensionality reduction phase, we proposed a model consisting of 2 neural networks, a generator and an autoencoder. These 2 networks are not trained in an adversarial way, like in a classical GAN scheme, but they are trained simultaneously in a sort of cooperative way. The generative network leads to produce synthetic instances starting from random uniform inputs. The goal of this network is to generate examples more and more similar to real input data. In our model, the generator has the primary objective of adaptively introducing noise into the training process of the 2 networks, to regularize the process and consequently increasing the model's resistance to overfitting. On the other side, the compression network is a denoising autoencoder that, firstly, in the encoding process, it learns how to encode all the input data into a lower dimensional space, and afterwards, in the decoding process, it learns how to reconstruct the input data back from the compressed encoded lattice space to a representation similar to the original input. In this slide, you can observe the architecture of the proposed model and the loss functions of the 2 involved networks. Zeta represents the random seed, G of zeta represents the synthetic data created by the generator, A of G of zeta represents the reconstructed synthetic data by the autoencoder, X represents the real data, and finally A of X represents the reconstructed real data by the autoencoder. As you can note, the generator tries to minimize the mean square error among the statistics of the generated instances and the statistics of the real instances, while the autoencoder tries to maximize the sum of the cosine similarity among the synthetic data and the reconstructed synthetic data, and of the cosine similarity among the real data and the reconstructed real data. Afterward, in the second step of GCTM, the clustering phase, we apply agglomerative hierarchical clustering for extract clusters of documents based on the previously obtained compressed representation. Later, in the third step of GCTM, the summarization phase, we extracted the most representative words for each of the previously computed cluster. Specifically, we define a custom weighting scheme, and later, for each cluster of documents, we extracted the top word based on the highest relevance scores. Essentially, the relevance score of a word W in a cluster C is defined like the ratio among the inner term frequency of W inside C and the square root of the global term frequency of W inside the whole collection. Finally, in the last step of GCTM, we refine the extracted topics through a technique based on word embeddings. To be specific, firstly, we calculated the embeddings on the input data through a simple word vectorization algorithm like word2vec. Then, for each topic, we consider a superset S of the top M words that we want to consider. S and M are two integer hyperparameters. Finally, for each topic, in an iterative way, we eliminated the most discordant words from the current superset S until we get exactly M words. In the following slides, we will show the results obtained after a comparative analysis. In particular, we compare two versions of our model, one with embedding optimization and one without embedding optimization, with other 5 recent models based on VAE and GAN. We tested these models on 3 common datasets and various specific metrics, varying the number of topics k. In this slide, you can observe the results computed on the 20 new groups dataset. In bold font, you can find the best result for the specific line metric. As you can note, GCTM with embedding optimization seem to have the better results. While in this slide you can observe the results computed on the International Movie Database Reviews dataset. Also in this case, GCTM with embedding optimization seems to have the better results. To conclude, in this slide you can observe the results computed on the Reuters dataset. In this case, the situation is more nuanced. However, the two versions of GCTM seem to have good performance in most cases. Moreover, we performed an ablation study. Our goal was to understand if the generative network was really useful in the dimensionality reduction phase or not. As you can see from the table, the generative part confers better performance to the overall system. So we can conclude the results part by showing an application of GCTM to a real use case. To be specific, we collected discussion threads associated to thyroid disease from an online health forum, and we extracted topics with GCTM. In the table on the left, you can see the top cluster words, while on the chart on the right, you can see the collocation on a two-dimensional space of all the extracted topics. To conclude, Generative Adversarial Networks and Variational AutoEncoders have been recently considered promising solutions for the complex unsupervised problem of topic modeling from unlabeled text. However, opposing agents in generative adversarial networks could cause problems of convergence, while, on the other side, autoencoders could tend to overfit. In this paper, we propose generative cooperative topic modeling. In this model, a generator and an autoencoder work in a cooperative way instead of opposing each other. This allows us to achieve faster convergence and promising performance. In the experimental section, we have shown that GCTM achieves good performance and faster convergence. We tested our model on 3 datasets, 6 cluster internal measures, and a variable number of topics. And moreover, we compare it with some of the most recent generative adversarial networks system and variational autoencoder systems. In this slide, you can see the list with all the presentation references. So, this is all. Thanks for your attention.